Hello everyone, and welcome to Physics Society and to the fourth talk this Michaelmas term. My name is Gia and I'm the president, and we're joined today by Akash, who's our academic officer. We're delighted to introduce you to our speaker, Carly, for her talk on Europa Clippers, Search for Life.
Thank you. And I apologize for the earlier time. I have two young kids at home, and 5 o'clock is traditionally when they have a big meltdown and I feed them. So I have to go home and do that. So I wanted to talk to you today about some work that I've been doing on a mission that's going to Europa. And I wanted to tell you, kind of explain all of the words I've just used, right? What is Europa? What is the mission? And why should we bother, really? And explain a little bit about that. So it might not come as any surprise that the world I'm showing you is Europa. It's a moon of Jupiter. And it's one of the reasons that I think it's really interesting is we think it could be a place that life could exist in our solar system outside of the Earth. Okay. Next step, get animation to work. Okay, so this is what I'm going to be talking about. So what is Europa? We've already touched on that. What does a world need to be habitable? When I talk about habitability, when I say that life might exist, what are the prerequisites that we use, and what are the assumptions that we make in those prerequisites, right? We only have an N of 1. We know that life exists on the Earth. We don't know where it exists elsewhere, and we don't know if it has a different evolutionary path. It probably does, if it has different requirements. Does Europa meet these criteria? And then I'm going to talk a little bit about the mission. So the mission that's going to Europa is called Europa Clipper. So we'll be talking a little bit about that. And then the logistics of it, right? So I'm not only involved in the science side, I'm also involved on the project management side of Europa Clipper. So thinking about how it's going to get there, what it's going to do when it's there, how are we going to take these observations has been a really important part of my research. And then what to look for, what sort of a way of keeping abreast of what's going on. Okay, so what is Europa? So here we go. Planetary Science 101, Jupiter. Io is the next one out. So all these 4 moons are called the Galilean moons. So they're the ones that Galileo was able to see, the moons of Jupiter, through his telescope. Out of order, this isn't to scale. Io, Europa, Ganymede, Callisto. Io is really quite close to Jupiter. It's rocky, it's full of volcanoes, and it gets squeezed and relaxed as it goes around its orbit around Jupiter. And its tides are about 100 meters high, right? So the average tides on the Earth are about 1 meter. So you know how much the sea goes up and down. There's no seas on Europa. The rock goes up and down about 100 meters as it goes around its orbit twice, right? So it goes up and down twice as it goes around its orbit. So really quite a nasty world to live in. Lots of sulfur, lots of noxious gas, not a great spot. Europa's a little bit further out, so it still gets some of this tidal energy, right? It still gets this squeezed and relaxed as it goes around Jupiter, but it's at a nice distance where it doesn't really cause a lot of harm. It just heats up that interior, and we'll talk a little bit about this. Ganymede is really interesting in its own right. It's the mission that JUICE is going to, which is the European mission, and we'll talk a little bit more about that. It's the only moon in the solar system with its own magnetic field, which is kind of interesting and talks a little bit about what's going on in its core. And Callisto is pretty interesting because it's really old. It's actually quite a nice counterpoint to the others. This, like I said, this scale's really wrong. Callisto is a long way out. It's got a very ancient and cratered surface and kind of gives you a better view into the history of the system than the others that have a lot more activity. And then the last mission that really was based in the Jupiter system was the Galileo spacecraft that deorbited in 2003. So it's time to go back. Okay, so Europa's surface. So this is a full global picture of Europa. I'm going to come around here so I can actually point to things. The first thing you can see is there's quite a lot going on, right? It's not a boring surface at all. So you can see there's some bright craters, and this is another crater, but it's got dark. So the surface is all water ice, and so when something comes in recently and hits it, the ejector that comes off of the surface is all water. And it leads to these bright rays. Anything in the outer solar system, if it's old, it tends to go red. There's lots of dust and stuff floating about that tends to have organics in that eventually become reddened. And so it sort of points to a different history, right? There's the browners are typically older surfaces in our solar system. That's not always true on Europa, but generally speaking, it is. Let's zoom in on a few bits. So if we zoom in on something called those ridged plains, and geologists and planetary scientists aren't always the most imaginative of people. We tend to call it like we see it. And so these are called ridge plains because they have ridges on them. And this double faulting is seen a lot in the outer solar system. And so we see it in regions where there's a fracture and you get material that's coming out through that fracture and depositing sort of either side of the exit. These are kind of interesting because you can see they're incredibly long, and there's also a coloration that goes with them, right? You can see that the ridges themselves are a lot redder than the planes. This chaos terrain is really interesting. So like I said, things get called what they look like. And so you have this sort of mottled terrain with ridges around it. And then this region that looks like there's been a sort of a crack, there's been a sort of a change in the surface with these blocks, right? These are icy blocks. You could think of them as water icebergs, really, that are all tilted on their side. This might have been a flow. This might have been, at some point, not liquid water because it's very cold and facing space, but something more akin to that, where we've had tilting of rocky material, of boulders, of icy boulders. And these bands, these are really interesting. So you can sort of obviously see what I mean, right? You've got clearly a surface here and a surface here that look quite similar, and then the surface in the middle looks very different. And you can see in some regions, it cuts across these ridges. So here it sort of flows over the ridges. But here, the ridges themselves cut over the bands. And that's telling you something about the order that these things happened in, right? So probably just looking at this, you could say, okay, this was probably here first, right? This long ridge up here. Then the band came in, and it cut that in half. And then afterwards, you had additional ridges formed. So this way, when we start looking at surfaces, you can get this idea of what the timeline for that surface alteration was, what things must have happened first, what things must have happened later. And we think that there's two ideas of what was happening here. And this video was made with a really stupid color scheme because red here means cold, right? It's really, really dumb. But anyway, just bear with me. So one of the ideas of what you're actually seeing is this is there's almost like continental drift, right? There's two regions that are being pulled away and there's upwelling that's happening between them. Let's see if this plays. Nope, come on, there we go, right. And this is a visualization of what might have been happening. So you have this cold surface, remember cold is red. And then these two plates are sort of pulling apart from one another. The material that's deeper in the ice, so it's further away from the ice, the coldness of space, so it's warmer, is able to then infill, and you end up with material so Europa has a subsurface ocean. We haven't touched on it yet, but you could possibly have things like ocean material getting closer to the surface in those regions because you've evacuated a space, you've made space for it. We don't know, these are all ideas. Another idea for these bands is that instead of it being two plates apart, you have a subduction zone. So instead of two plates going away from each other, you could be looking at ripples and bands that form because one plate is going underneath another. This might be, we don't really know why you would end up with plates that are moving on Europa. It's got a very different setup, but this is something else that could explain it. Lenticulae are pretty interesting. So lenticulae are these look like moles, right? These little brown dots that occur across the surface of Europa in very discrete regions. You tend to have a patch of them, and then nothing, and then a little patch more. We think these might be. Let's see. I'm not actually in present. Let me just see if I can exit this real quick and see if I can do. Then I can. There we go. And then I think I have to swap displays. Give me one sec. Because then I can see whether I do have animations or not. There we go. I know I have. All right, there we are. So this animation, which isn't working now. Nope. OK. So we think what's happening here, maybe it was never an animation, is similar dynamics, right? So Europa, we know it's getting this heat from Jupiter. It's heating up its core. The ocean that sits, we think, connected with its rocky surface is much warmer, right? Liquid water, even with some antifreeze, is going to be 0 degrees Celsius, give or take a few. The coldness of space is touching there, so it's at 2 to 4 Kelvin with some daylight, whatever. So it probably brings it up to more like 30 or 40. But there's a huge temperature gradient here. That's the point, really. And so you're going to end up with some ice movement. And it could be that we think lenticulae, where we've had the sort of top of a bulb of water that's come up through the surface. This is a view in of that chaos terrain. This is a zoom in of that region. Like I said, it's a real mishmash of stuff. So it's got a lot of it almost looks like footprints here, but this is still, hundreds of kilometers across. But you can see one of the things that dominate is it really doesn't have a single process that's going on. So maybe this is a particularly active region. There's been multiple processes that have changed it over the years. But when we look to the Earth, and we do that a lot when we start looking in the outer solar system, we look for Earth analogs. If you look at chaos terrain on Europa and you look at ice flows on the Earth, you can just visually see there's a lot of similarities. And you have to be careful with that because sometimes things don't scale. But there's this really nice movie. Let's see if I can get this one working. Yeah, okay. Of ice flow on the Earth, so it's a bit sped up. You can see the clock down here. This is taken, I think it's somewhere off of Antarctica. But you can see there's this huge ice shears, right, that come off, and they kind of create these ice boulders, if you like these floating icebergs. And then when it all stops and it all freezes, you kind of get these tilted ice flows. And when you zoom out on that, it actually looks like a lot of what we see on Europa. So it could be at some point there was this moment of energy release and things flowed on the surface and then quickly refroze. Like I say, I mean, probably not completely comparable with this, but you kind of get the idea. One of the things that we don't know if Europa has are plumes. So this is on the right-hand side, you're looking at some Hubble Space Telescope data. And so the limb has obviously been overlaid. And what you're looking at is hydrogen. So they were looking for hydrogen emission. And you can see there's this brighter spot down here, right? So the background, you can sort of, if you go up here for contrast, you can see it's mostly black and light blues. There's always a bit of error in data. This is where Europa lays. And there's this really bright spot off the edge of Europa. And one explanation for that bright spot, maybe it was something with the instrument, maybe it was something else that was going on, but one possible explanation that's been pitched is that Europa could have plumes. Okay, this is obviously an artist's impression of what that might look like, but they would be, if they were there, they would be water ice, we think, because that's mostly what Europa is made of, and it would be coming off the limb. Now, subsequently, there's been some studies, and some of them are quite compelling. So not every time we look at Europa, we see this. So if they are going off, they're sporadic. They happen sometimes, they don't happen other times. We don't really know why they would happen at some time. We've looked at where Europa would be in the orbit, what time of, whether the sun was particularly active, all those sorts of, tried to correlate it with lots of things and haven't found something that was very satisfactory. But the fact that we see them, we see it in this data set, and observations that have subsequently gone back to look, some have seen it, some haven't. And so one of, I think, the compelling things was if you reanalyze Galileo data, you can see traces of plumes in the magnetosphere measurements that were made. It disrupts Jupiter's magnetosphere. And so I think one of the things we'll be looking for in Europa Clipper is to look to see whether we can see plumes going off on Europa. This is its interior. I've kind of already touched a little bit on that. So we know it's got a magnetic core. It's got a rocky outer layer, and then this global ocean. And so the Galileo mission did a really good job on figuring out that there's definitely an ocean there. It's definitely global. And then this thick icy crust. And this is, tens to hundreds of kilometers thick. And so one of the things that would be really cool if plumes do exist, especially if they're connected with the ocean, is if there's life on Europa, it's probably in the ocean. Right, when we have tidal heating, Europa's moving around its elliptical orbit. At some point, it's further from Jupiter, and everything sort of relaxes. At some point, it's closer to Jupiter, and Jupiter's massive, right? Gravitational effect is huge. It squeezes this core, and that provides, and then as it relaxes, that gets dissipated as heat. Right, so that's the way that this ocean is maintained. So it's getting heat from the core, and it's being protected, a bit like a thermal blanket, from the coldness of space by this icy crust. But if we want to see where life is happening, and it's happening in the oceans, you've got some technical challenges. You've got some ethical ones too, but you also have some technical challenges. Right, just getting through kilometers of incredibly hard ice. Right, the ice here is so hard and so cold that you can make mountains out of it. Right, it really forms the bedrock in Europa. It's not like ice that we get on the Earth. It's not nice fluffy snow that you could dig through. Right, you've got to think of the ice here as almost rock-like. So if you want to dig through kilometers and kilometers of ice to get to your ocean, that's going to be a really big technical challenge. And then when you do, you're encountering an ocean that you've never encountered before that may or may not have life. Right? How do you make sure that your equipment is clean enough that you're not going to disrupt that life, potentially damaging it or killing it before you've even sampled it? But if there's a plume, magically if there's a plume, perhaps it's going to carry some of that ocean material with it out into space where you can just go and sample it there, or you don't have to go through these kilometers of ice to do so. And ethically, it's better, right? You're not disrupting that ecosystem. So, where is habitable? This sort of brings us on to this question of habitability. And usually when I give this talk, I tell people not to be scared of this graph, but you're all physicists, so I think we'll be fine, right? Okay, so let's talk it through. So pH, right? So this is acid, this is not acid, right? This is alkaline. Temperatures on the y-axis. And most things that we know and love are in this green box, right? So our saliva is slap bang in the middle, blood slightly further to the right, we have water, rain, but one of the things that astrobiologists have been doing for a long time is trying to figure out where else on this spectrum does life exist, right? And so if you go, and so some of this other information tells you where we've found life that exists, right? So the red spot is we've got some stomach acid, we've got, there's brines that exist where we've found very, very cold life. So this is temperatures, this is -20. If you go to the Himalayas, I guess there's midges that live there. And you can see Yellowstone is crazy, so it gets very hot, it gets very acidic, and yet it's full of life, right? So there's quite a lot of ranges that life can exist just on the Earth, right? Outside of this nice green habitable zone. And actually, if you take this to an extremity, right, they've taken tardigrades up. There's actually some on the moon, right? There's an Israeli mission that took some, and it was supposed to, so these are, you could think of them as incredibly small extremophiles, right? But it's very life. Like if you saw one wiggling about, you'd go, yep, that's life. And they took them to the moon with the idea that they were going to land them safely and it was going to be nice. And they would see whether they could exist. But the mission crashed. And so they're now just life on the moon, and we put it there. And in theory, they need water to be activated, and there's not much water on the moon. So we're hopeful that they're not going to become this new dominant superpower on the moon. But the point is that there's lots of extremophiles that exist. We've found some on the outside of the International Space Station, right? Like life can exist in really weird places. So when we apply our knowledge and understanding and our biases about what life is and where life can exist, we have to be a little bit careful with that, right? We can't just assume that because we like it moderate in all ways, like a moderate pH, a moderate temperature, we don't like it too hot, we don't like it too cold. It's the Goldilocks, the slightly warm porridge of life's ability to survive. But I think it is also really useful to compare it to the Earth. Like, whilst acknowledging we only have an N of 1, we do have something to compare it to. And so when we're thinking about where life could exist, this is sort of what we think might be a happy zone. Okay, so what do we need for habitability? Right, the first thing is an energy source. Right? Most of the time that's sunlight. On the Earth, a lot of it's sunlight, but not everywhere. Right? And I will go on to talk about where on the Earth we don't have light, and yet we still see life. For example, in the deep trenches of the Earth, right? If you go to the Marinara Trench and you go right to the bottom, and there's these black deep smokers, and I think I have a video later on, you just need energy, and that's teeming with life. And if you look at a video and you go, well, that looks a bit like a crab, and that looks a bit like a lobster, and they're definitely life. You don't have to have someone that's specialized in biology in order for you to go, there's life. And that's what I'm talking about when we talk about life in the outer solar system. Bacteria are nice and all, but wouldn't it be fun to find crabby things? And you can find crabby things if you have an energy source. Liquid water, and this chinops. We've probably learned about that back in the day if it's not been familiar. So things like we need carbon, we need nitrogen, we need phosphorus in order to make, as we understand it, the building blocks for life, for the cells to exist in the first place. And Europa has all those things, right? Europa has, we know, but studying its surface, it has those important chemistries. We know that it has a liquid water ocean, and we know that it has energy that may or may not manifest as these black smokers. But why not, right? We see them on the Earth, why not there too? But the trouble is this big ice sheet. In actual fact, Europa has more water than the Earth does, which is a bit bonkers. So if you take all of the water that's on the Earth and you make it into a dot, it looks about that big. Mars doesn't even get a dot because it's rubbish. And, and Europa has about twice the amount. Right? It's mostly water. It's mostly water ice, and then it's liquid water ocean. So there's no problem with hitting we need some water on Europa. Let's talk about energy. So I've talked a little bit about tidal flexing already, but this is an animation, obviously, of how it might work. So you have Jupiter moving in the background, it's getting closer and further away, and Europa is squishing and releasing, and that gives its energy source. Okay, so we've got 2 down. This is CHNOP, so our carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. I'd forgotten what S was, so that's great. And it's all there, right? We need them in order to build our cells. We need them to build lipids and I'm going to look at nucleic acid and proteins and all the things that we need in order to survive and for life to be there. And we see that. So my question is, I guess, what's the last thing it needs? This isn't rhetorical. Come on, one of you's brave. Go ahead.
Some sort of mechanism to drive it towards, I'll say evolution.
Yeah, that's basically right. You need time, right? You need to allow evolution to happen. You need something that's going to happen. If you had all those things instantly, it doesn't mean you're going to get life tomorrow, right? So one of the things we worry about is how long ago something formed. Right? Has it had time? Has it had a stable environment? Has it always had those things? Perhaps at some point, for some weird reason, Europa didn't have all of those chemicals. Perhaps it didn't have enough energy in order to maintain a liquid water ocean. We don't know. We don't know what life on Europa looked like 1 billion years ago. Right? So whether something has had time to evolve is really important. But from what we understand, it probably did. Right? Europa is in a really stable part of space. We've seen that from its sister moon, from Callisto, it's really ancient terrain. So that probably means that Jupiter hasn't, sometimes systems we know, basically their whole moon systems collapse. And a bit like we see rings at Saturn, they sort of destroy each other, you end up with a rubble pile, and those moons get remade. But when we look at Callisto, which is this really old version of Europa, right, we can see that it's very old from its cratering record. We see that it has really, really big craters, which tends to mean they're very old craters. And so if Callisto still has them, Europa probably did have them, but because it has liquid water, it probably has some geology, active geology going on. Those craters have been eroded. But we think that that means it's had time to evolve. So, yes, maybe wiggly things. And that's saying the same thing. So this is a video of that black smoker. Let's get this playing. So perhaps life looks something like this, right? So this is, remember, this is in the deep of the ocean. The only reason you're able to see anything is because the cameras have videos with lights with them. And so you can see a bunch of things without looking too hard that do look like there's wiggly things in here, lots of wiggly things, like shrimpy things and crabby things. And that's definitely a crabby thing. I'm not a biologist, but I'm going to go out on a limb. But there's this energy, right? There's this, and where life can exist, so no light, light doesn't exist here, but there's energy, and there's water, and there's these chemicals. And so perhaps that's the same, perhaps something like this is going on under Europa's surface, but we just can't see it because there's 20, 30 kilometers of ice between what we can see and what's going on down there. Okay. So let's talk a bit about the Europa Clipper. So this is the spacecraft. It's got really big solar panels. We're a long way from the sun. We want to do lots of cool stuff. We need power to do that, big solar panels. And so we're carrying cameras. That's not surprising, right? We want to see what's going on. We want to look at the surface in unprecedented detail. We've got a spectrometer, which is to look at the surface composition. So we're going to understand better about what trace elements there are and how that contributes towards its story about habitability. This is my baby, so E-Themis is the thermal instrument. I'm mainly interested in the thermal signatures of the surface, so looking for evidence of plumes, looking for hotspots, Understanding surface composition through thermal measurements is my bag. So I'm helping plan some of those observations, and this is the team I'm on. SUDA is the dust analyzer, which is sort of understanding the bigger context of what Europa is experiencing. We have a mass spectrometer, so as we fly through plumes, or if we fly through its dust tail and things like that, we'll be able to sample in situ sampling as we go. UV spectrograph, again for composition. You can also use that to look for really tenuous atmospheres. Radar's cool. This is going to be really, really interesting. So even though I'm a thermal person, I think flying radar to an icy world is going to be really awesome, because we don't know. So one of the things we don't really know is how pure the ice is, and that really changes how well you see that reflection. But we have two different radar systems that have different wavelengths, and so we think we're going to be able to see the near surface, which is going to be really interesting for understanding things like how that chaotic, how deep does that chaos terrain go? And then one that can hopefully see right down to the bottom of the ice shell to give us an idea of the structure of the full ice shell. And this has never been flown. Radar is intensely power hungry. It needs a lot of resources. It gives you a lot of data and takes a lot of power to run. So they're not really flown on any missions that aren't the biggest mission going because of those reasons. So this is going to be really cool. And then we have plasma instruments for looking at the surrounding environment and magnetospheres for similar reasoning. So these are what we're going to be trying to look at. We're looking at the ice shell in the ocean. I've already talked about that. Activity being the plumes and maybe a search for plumes. Composition and geology we've sort of already talked about. But reconnaissance is an interesting one, right? There's this understanding that you can do a lot from remote sensing, from being a distance away from a surface and then looking at it. But we want to probably at some point go back to Europa with some form of lander. And in order to know where to land, you need to know what the surface is really like in very high detail, right? It's no good knowing what the structure is on kilometer scale, because that's not relevant, right? You want to know how bumpy is it in, the area of this desk, because that's how big your lander's probably going to be. And you want to make sure you've got a safe space to land that thing on. And you can't do that from the Earth. Europa's just too far away. Even with the amazing instruments we have now, you can't resolve things that are, less than tens of meters big without going there. So this for human for scale. This is the Europa Clipper before it was launched. It was put together at the Jet Propulsion Lab in California, and I got to go and see it, which was pretty fun. And so we have a massive dish for talking to the Earth, because if you've taken all that data, you darn well want to be able to downlink it and send it back. And then all this protective coating goes on to make sure it's thermally. It's got a uniform thermal signature, so it sort of conducts heat around. And then we stick it on a rocket. And so this is the size of the Europa Clipper spacecraft. So it was launched on an SLS Block 1. No, so it wasn't actually in the end. So this is the size of Europa Clipper. This is a very American slide, sorry. I totally stole this from JPL. If you've ever seen the Statue of Liberty, that gives you something. If not, Europa Clipper is pretty darn big. Especially when its wings are unfurled. It's about the size of a basketball court, which you might have seen back in gym, back in the day. So it launched on, it was supposed to launch on the SLS, but didn't, which was good, I think, because you never want to be one of the firsts of anything. So it launched on a Falcon Heavy in the end, and it was great. So, but what was funny, and I've got a bit of a personal story about the launch, is we're all set, right? The spacecraft's been flown down to Kennedy Space Center in Florida from the Jet Propulsion Laboratory on the East Coast, in LA on the West Coast of America. We've been waiting for this for a long time. We have this launch window that opens up, and you try and launch as quickly as you can, right? Because you want to get it out of here for lots of reasons, mainly for cost. And I'm due to fly out on the Sunday, and I'm looking at the weather and the news, and there's talk of a hurricane coming through Florida. I talk to my brother and I say, well, they haven't scrubbed the launch yet. The launch is still planned to go ahead. I don't know whether to get on the plane. My brother says, I don't really know about that, but it seems like not flying into the eye of a hurricane is probably a good idea. And it was like, yeah, okay, Dave, which is his name, so it worked. And so I didn't fly out that day and waited. And so most of the crew that were already there, I was flying out a bit late, had to sit through a hurricane. And this was the track of the Hurricane Milton. So it formed in the Gulf of Mexico and moved up through. And it's a bit hard. So this is the weather.gov So as it reaches, it gets stronger and stronger and stronger, and then it hits the coast of Florida. And the eye of the hurricane went over the launch pad exactly at the beginning of our launch window. So needless to say, I mean, it would have been truly epic to launch through the eye of the hurricane. And if we were a Hollywood movie, that's exactly what we would have done. But as it was, we didn't. So we didn't do that. And instead, we launched a few days later, and I did fly out in time for it, taking my brother's advice of waiting. And it's a bit hard to see. These are people, this is the Europa Clipper logo. This is the Europa Clipper spacecraft in the background on this. This is Banana Creek. So this is as close as scientists can get that aren't in the no-go. There's a go, no-go area, which is a little bit closer. So that's where the lead of the mission is. But this is all where the scientists were. And this is our blow-up moon of Europa. And we were waiting for the launch. And it was a beautiful day, beautiful, nice and clear. And there's some really great movies of the launch. Mine isn't, but it is mine. So I'm going to show you that. And so let's see how I get this to go. Let's see. And there's no video. Okay. Scientists getting very excited, including myself. So thing launching. The thing to take into mind is the fiery bit stays down and the pointy bit stays up. That's what we're looking for in a launch, really. So yeah, fiery bit continues to stay down. Day is good. Life is good. I mean, you have to remember, right, we've spent the last decade making this thing. And we have one chance for it to launch, right? Once the engines start ignition, there's no going back, you're going. And so you've just got to hope that it continues to go really well. Like, it's completely out of your hands, right? You're just trusting the people at SpaceX with your multi-billion-dollar spacecraft. And that day they did good. So like I said, other better pictures are available, and that's probably one of them. Right, so what now? So we launched, that was great. One of the things we have to worry about is Europa is very close to Jupiter, right? We've already talked about that. Jupiter's got this massive magnetosphere. It's absolutely huge. I think it would be the biggest thing that we could see in the sky if we could see it, but we can't, right? And so that's great in lots of ways. It enables us to study Europa in ways that we couldn't see, but it's really, really bad for spacecraft, right? Because you're bombarding it with high energy particles all the time. They're getting funneled down its magnetic field. So whilst we want to study Europa is actually a really bad place to spend a spacecraft. So you've got this kind of catch-22 thing going on. So what we're doing is not orbiting Europa, but instead we're flying by it. And this is the ground tracks of all the tours. So you really want to get a good sample, right? You want to see everywhere on Europa. You don't just want to see like the equator or just the poles, but we want to see all over. And these are the ground tracks that you end up with. I think this is a movie. There we go. So these are the ground tracks. So we showed one of the things we've been doing for the last 3 or 4 years is trying to figure out optimizing this, right? Because each instrument has its own, but we want to be at this altitude, and we want to see it at nighttime, and we want to see it at daytime, and we want to see it. So trying to figure out how to make everyone equally unhappy, right? That's the takeaway, right? And I think we're pretty close to it. We'll probably discover something and then have to rewrite all of this, but you've got to have a plan, right? You've got to have a starting plan. So this is our starting plan of where we're going to see. So we launched, excellent. Not in a hurricane, excellent. We did one Mars gravity assist, which was kind of fun. So we took, with the thermal instrument that I'm involved in, we took some observations of Mars. And I had a colleague email me and say, these observations are really disappointing. And you're like, that's great. That's exactly what we wanted to hear from this $1 million mission that we've sent. But the point they were saying was, we've seen Mars and the thermal at much better resolutions, right? In different ways, And my point was, it doesn't matter. What this observation shows is that our instrument works. It's not designed to work at Mars. Of course it's too hot. We're not looking at Mars. But it shows that our instrument's working. And I think that was a great indication of how your own, I don't know, you can look at a data set and two people can take away very different things. To me, it was one of the most glorious things I've seen in a long time. And for her, it is actually high-rise does better. And you're like, yeah, okay. But we're not flying high-rise to Europa, so what are you going to do? And then we're going to go on and we do an Earth gravity assist. So it's kind of a funny way to get to Jupiter is you come back to the Earth. And then we go out and we have orbit insertion in 2030. So like I was being asked earlier, there's a bit of a wait. And that's always true in outer planets research, you kind of get used to it. I flew to Pluto. Well, I didn't personally, but we sent a mission there, and it took 9 years, right? So there's a wait, and it's part of the reason that actually right now there's a bit of a dearth in outer solar system missions. We have going to Europa, but that's about it. And so there's a long time to wait. So even if we started something now, we're not going to get there for another 10, 15, 20 years. But this is going to be exciting when it gets there. Let's see, I think this is a video. Okay, is it playing? No, it's not. Okay. And I realize this talk's too long for the time event allocated, so I'll show you some videos and then shut up. But this is just an animator's, an artist's concept of what Europa Clipper will look like as it flies past Europa. I think it's pretty cool. So you can see we've got really long booms. Every time you fly a magnetometer or a radar, you need really long booms. You need to get it away from your spacecraft. The spacecrafts tend to have their own magnetic field, their own magnetic signature, and so you need those to be on a boom. And so that's it flying over Jupiter. We're not allowed to talk about Jupiter science at the moment. Of course, we'll do some because we're scientists, and if there's a really big target in the sky, we're definitely going to look at it. But without wishing to stray into politics, the US is having some interesting times right now. So we're certainly not allowed to talk about extending the budget and to do science that we aren't specified to do. So right now, we can talk about Europa and the Europa science, but I'm sure at some point there'll be some sneaky observations of Jupiter for calibration, which is one way that we'll get to see it. But I think it's going to be kind of fun. All right, so this is our tour. We come in, and like I say, we don't orbit Europa, we orbit Jupiter, and we try to spend as little time as close to Jupiter as we possibly can. It's got this enormous magnetic field, very dangerous. So we come in, swoop past Europa and out again. And so we've got a lot of time each orbit to downlink that data. So as we come in, we start taking observations, we put them on our hard drive, and then as we move out of Jupiter's system, we'll then downlink the data and hopefully clear it by the time we do the next one. We do get some flybys of the other moons. Again, we're not allowed to talk about those, but I'm sure for calibration, we'll be able to look at those a little bit sometimes, maybe, if no one's looking. That'd be great. So what next? There will be some parts, what we can see from the Earth is going to do an Earth flyby, which will be pretty fun. There's still a few trajectory correction maneuvers, so we're not actually sure what part of the Earth will be able to view Europa Clipper, because it will depend exactly on the timing, obviously. But in 2026, we're expecting at least some part of the Earth to be able to see it, which would be kind of fun. And there's lots of resources. So if you're interested in following along, there's all the right things. So there's a QR code here, and I can share these slides if you want to send them around. But there's some really nice JPL-led, especially if you do outreach, there's a really nice outreach pack. So there's coloring in, and for a little bit older kids, some more like lessons on how to do things, some paper models that you can print out and get kids to make. Europa models and things like that, which I have made. It's quite tricky, but I think for older kids it would be fun. So those are the relevant hashtags. I don't know why there's not a blue sky one on there, but I think there is one, so you can find it. So with that, I think we've got time for questions. Sorry, it went on a bit. Thanks. That is the end of the talk. Sorry, that wasn't clear. Yes. Yeah.
I have several questions. I mean, I think it's really, really cool that you got the chance to, work on these missions. So I have a few questions just about the logistics of all of this. Basically, okay, what is an Earth gravity assist? How do you work? How do you plan that? And then
That's
also
a fair question.
A little bit about the expected lifespan of the mission. And when you're planning things like that, are there any unforeseeable events that you plan for? Do you have a plan B, plan C? What if, an asteroid comes, I don't know.
Yep, excellent questions. So the first part, an Earth gravity assist is where you basically use it as like a slingshot. So you come in and you circle a body and you pick up, and as its gravity speeds you up, you take that and you sort of use it to speed up your spacecraft. It's a really good way of getting to the outer solar system. Lots of people use a Jupiter gravity assist. So I was on New Horizons and we went to Pluto, we flew past Jupiter. And it makes the trajectory quite tricky because you have to hit kind of a keyhole space in order, you don't want to get so close that you get pulled in, but you don't want to be so far away that you're not optimizing that speeding up either. So that's what that is. And it can be anything that's got a mass. JUICE actually recently did one where they used both the Earth and the Moon's gravity. So they did an Earth and a lunar gravity assist, which is quite unusual. So people are getting clever at this, but it's kind of a way of just for free, basically, right? You're not spending propellant on it, you're just using time. So that's that. There's always things, right? People are making this. There's people involved. Anytime you involve people, things are going to go wrong. And so one of the things that we found on Europa Clipper, so it's in this high radiation environment, and we'd used components that were rated for a high energy environment, right? And then at a conference I wasn't at, someone from the US military at a water cooler, basically at coffee break, sidled up to someone on Europa Clipper and went, you know those transistors you're using? Have you tested them for radiation hardness? And we went, no, because the manufacturer said, and they've been used in space, and we didn't test every component, right? At some point, you've got to use trusted sources. And they went, yeah, we've tested them. You might want to have a look. And so they did, and they failed. But these transistors are everywhere in the spacecraft, right? And the spacecraft at this point has been put together. It's under MLR, right? We're not in components phase, where we've bolted it all together. We've tested it. It's calibrated. And so then there was this huge moment of okay, step one, where are the transistors? And every instrument went, well, we use those too. Yeah, they're here, and we use them too. And then you have the plan B. It's like, okay, what do we do? So there's the big ones. You don't want it to be in anything that's going to kill your mission. So if an instrument fails, bummer. If your propulsion system fails, major bummer, right? So communications, propulsion. You could think, all those things that keep your mission alive are a big deal. And so they went through and replaced those that made sense. They didn't replace a lot of them. And so the way you get around that is then you say, okay, well, actually, our nominal life mission was 5 years. That was if we reach 5 years, it was a success. Well, we're going to call that 3. So you still get to succeed. It just takes you less time. And so there are sort of these ways of getting around it. But actually, it was considered to be more risky to take the spacecraft to bits, to take out all these transistors, to replace them all. What damage are you doing in the interim? And one of the testing that we found, when the testing was done, the way that these transistors failed was they failed open, so that the circuit's still completed. And so at that point, you're like, okay, so if the ones that go out in the communications, it's still going to be able to communicate. And we'll just have to, from an operations perspective, we'll have to just change the way we talk to the spacecraft. But we'll still be able to talk to the spacecraft. And so that's a success, right? So there's lots of plans, D, E, F, G, and yeah, for sure. And some of them you kind of know are going to come. There's always something. And some of them, like the subtle word in your ear at a water cooler that changes the next 6 months of your life is less well known. I'm on Lucy, which is another NASA mission that has solar panels. And it launched from the Cape, and it was great. And we got word that the solar panels are unfurled, and you're like, brilliant, we're power positive, excellent. And what happened was they had unfurled, but only one of them had locked. So they have circular ones. So this is my I'm a little teapot dance, right? So one had come and it locked, and the other one had come and was like this, right? And if you have a spacecraft that's got a floppy bit, that's a bad time, right? So when we did, so okay, we've launched, right? We're power positive. Let's not do anything. Let's model what's going to happen. And when we fired the main engines in the model, the whole spacecraft did this sort of wave across it. And again, I'm not a structural engineer, but that looked like a bad time. And so we spent the next 6 months figuring out what happened, how we could correct it, how much we needed to correct it. And that was kind of a really interesting process. So what happened is there's a line, there's a bit like a fishing line, right? You reel it in, and that slowly pulls the mechanism in. And what happened is the reel had come off the spool. So it was getting harder and harder and harder for it to reel it in. And at some point, the tolerance had been reached and it stopped, right? And so the first thing was you go back to the engineering and you say, okay, you're engineers. I know that you've built in more tolerance than you've told us about because you're engineers. So how much can we really pull on this? And they go, okay, try this much and it'll be fine. And so you do that and it unfurls a little bit more. And then you say, okay, I know you guys better than that. What's the real answer? And they go, yeah, all right, you can have that. And then at some point they go, no, don't do it anymore, because if your reel breaks, then you're in big trouble, right? So there was a little bit of that going on. And the trouble we had actually with that mission is that the last bit required a bit of an action. So on a microwave, if you shut the door, there's sort of, you can swing it and then you have to click it. But and we could never get it over the click. But we got it to a point where actually it was unfurled enough that we fired the main engines and the spacecraft survived. So good enough. But there are always things you don't know. And sometimes you think that they're good. Like we were told that everything's unfurled and it's locked and we're good to go. So everyone went for breakfast. And then the PI gets a call and you see his face fall and you're like, oh no, what? Like, no. And then that's what we spent the next 6 months doing. But that's where having a lot of redundancy on the team, so a lot of great people that you can call on, working with partners that can staff up, like this was with Lockheed Martin. They're a big organization. They just threw everything at it and we fixed it. So pretty amazing to see. Sorry, that was a really long answer, but yeah. Yeah.
You mentioned earlier about the uncertainty whether you had stayed on the vault to have been there for that long, whether that would influence the chance of that. Does the orbital resonance structure of the close-in Galilean moons make you more confident in that? Yeah,
so the moons themselves are in resonance with one another. So like Io goes around once, or whatever, whichever way around it is. Europa, I think it's like it goes from so the closer you are, the quicker it goes around. But I think for every one that Callisto goes around, like Io might go around 3 or 4 times, but they all at some point line up. Right, and they do that. It takes quite a long time to do that, but they do that because eventually you sort of end up in a very energetically stable configuration. But that takes time for it to happen. So again, yes, absolutely. So the fact that Callisto's old, the fact that this whole system is very stable, it's in this very stable configuration, is helpful. And the fact that we see the whole Jupiter system as being something that was very stable. It's got these Trojan moons as well that you would only get if the system's stable. So there's lots of reasons to think, like you say, that Europa's been there a long time and it's been undamaged. And yeah, that's a great question. Yeah.
So I've got a couple, and they're both about those sort of red bands, which you're doing. So one of the models you had about that, was a possibility was essentially like a ocean ridge.
Yep.
With 2 scraping plates and upwelling.
Yeah.
And then that would imply that the upwelling being in the centre, which I assume would be the red band.
Yep.
That would be younger.
Yep.
So how would that then become red? Because you then make that's the whole.
Yeah. So that's what I said, right? So usually things in the outer solar system are red because they're old. Europa does have some weirdness in that regard. So typically, the way things become red is typically they've got some organics in them. And so you photolize them, it allows you to see sunlight or Lyman alpha or some other form of radiation that makes it more red. And you can do that in a lab, that's been quite well proven. So on Pluto, for example, the equatorial band around that's really heavily cratered is incredibly red, really dark, very from this process. So that's what we're used to seeing. On Europa, this clearly isn't true, right? There's no way that, for example, this has to be younger than this, right? And yet this is white and this is red, right? So it's pointing to the fact that there's a compositional difference, but it's not compositionally different for the reasons that we're used to in the outer solar system, right? It's not because it's already been covered, it's had millions of years to accumulate dust, which eventually has been, modified, blah, 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 blah. It's probably indicating that, there's the composition of whatever's upwelled here is redder. And why, I don't know, right? It's, I know this is really stupid. At some point, I didn't make the graphic, I'd like that known, but it's a really cool graphic other than the colors are wrong. So like, why is this red? I don't have a simple answer to that. I don't know. I don't know if anyone knows, to be honest. But one of the things we're going to be able to do, we've previously not had a very high resolution spectrometer. So we've not been able to say the composition of this is X and the composition of this is Y, right? You can probably say the composition of the whole square is got these components to it. But I think one of the things we'll be able to do with Europa Clipper is to really get that at a high resolution. And that's where you can start saying, this has got this additional molecule. This must mean, well, I don't know, whatever it means. But the white here we tend to think of it as being more waterized rich, and the red is more hydrocarbon rich. But like, why that would be the case here and not here is, I don't know if anyone knows the answer to that. Did you have two questions, or were they sort of encapsulated in that response?
The other one was almost about the other method you were mentioning about the subduction.
Yeah, this one.
Because how you put it there, it almost looks as if you imagine there, almost like wrinkles, I guess you could say, like mountains.
Yeah.
Could you use the length scale of the let's say the waves of the mountains to determine the ice length or something?
You could. Actually, a lot of the problems we have doing those sorts of measurements is that they're really hard to create this ice in the lab. So we don't actually know the fundamental properties of ice at 50 Kelvin in a vacuum very well. Right? But partly because no one needs it, right? Like it hasn't come up before much. And so one of the things I'm trying to do in my ice lab is exactly those sorts of tests. Like what are the thermophysical properties? What are the basic properties of ice under these conditions? And it's not the like 0.001 Kelvin ice that's sort of super cool and it's the bog standard, what does normal, IH ice look like at 50K? And I think once we have those models are going to get good enough to say something useful. I don't think it is this. I think that, I don't know. The other upwelling one, it looks to me more like sort of an ocean ridge trench where things have been pulled apart, but I'm not a geologist. That's just what I think. So.
I was going to say, the way they've sort of drawn that there, it almost looks like an accretion wedge.
Yeah. Yeah, with a clear difference in topography as well, right? You'd have a sort of an upwelling. I don't know if the bands are necessarily associated with that, like rise. But again, we'll have better DEM, so we'll have better elevation models when we've got good stereo and observations. All right. Yeah, go ahead.
Could you talk a little about how we know the basic structure of Europa, like how we know it's a liquid ocean?
Yes. So let's see if I can find a picture of, so the ice bit's quite easy, right? You can see that bit. There's two usual ways that you can understand what's going on beneath the surface. So the first is called libration. And what you do is you take you know where your spacecraft is and you take images of the surface. And if something's tidally locked, right, you would expect, which Europa is to Jupiter, so that means the same face is always facing Jupiter, like the Earth's moon, right? Like the same side of the moon is always facing us. Then that should remain, if it's all solid, that would remain the same, right? But what actually happens on Europa, and you can see it, is that there's a slight tilt, right? It moves, the shell moves a little bit as it moves around. It's very, very subtle. But if you know your spacecraft and you know where you're pointing very well, you can see that change. Okay, so that's the first indicator that there's something that's sort of like a lubricant, right, between the solid core and the outer shell. The shell's almost it's like spinning up the middle, right? And the surface takes a little bit longer to follow. The second thing was from the magnetic field. And magnetic field, Jupiter's magnetic field, as I said, is incredibly strong. If you throw a magnetometer near Europa, you can see how Europa changes the magnetic field. And the signature, if it moves through liquid, is different to the signature if it moves through a solid. And that's the real linchpin. That's the one that really settled it, that Europa definitely has a subsurface ocean. And we did the same thing. The same thing was done on the Cassini mission for Enceladus, which is Saturn's version of Europa. And it's pretty, you can't really explain that signature without an ocean. So that's how you explain the ocean. Getting the ice thickness is tricky, and it's an estimate right now. There are ways of getting at it. Flying radar is obviously the best way to do it, and so we'll know that a lot more accurately soon. You can start modeling. We know what the density profile is of Europa, so you can start playing games of how much water are you allowed and how much rock do you need in order to meet that density profile. So literally how much has Europa pulled on a spacecraft as it flew by? How much did its trajectory get moved by virtue of being close to the body? And so that kind of gives you an idea of what the rock and the core and the ice, the water ratio is. How you get to the core is, again, I think it's through gravity. That's not my area of expertise. But again, if you take these measurements and you see them over and over again, how much has Europa pulled it away, you kind of get a sense of what metallic core, how much mass you need in order to make that deviation. And then that, once you put that into models that actually show what the temperatures and pressures are going to be like, you kind of start getting, you can use your real world constraints in order to say what's probably going on. This is still a pictogram, like we haven't obviously measured it. There's a lot of error bars in this that aren't shown, but it's probably something along these lines to explain the observations that we have. Does that make sense? A bit hand wavy. Okay. Yeah.
There were some repercussions in there about a Europa Lambda concept. Is there anything other than the politicians won't give us money as to why that wouldn't happen in the near future?
Yeah. So the quick answer is no, right? If everything can be solved with time and money, it's just time and money. Yeah. It's an interesting problem though, right? Like if you think a world is habitable, should you be landing on it? Should you do everything in your power to explore it without landing on it first? And so I think there is a little bit of give and take there. Saying that, I'm involved in, and the next ESA large class mission will be going to Saturn's moon Europa, Saturn's moon Enceladus, sorry, and it will have a lander. And so we're talking about that, like how can we make it as safe as we possibly can be? I'm still not sure the lander for Enceladus. I still think we should be doing flume flybys, but again, I'm not the minister that's going to be making those decisions. Most things are just time and money, but I think there is a little bit of scientists trying to be a bit cautious about. And so this is really like I said, one of the goals is reconnaissance. And so I think there'll be a lot more political will if we can say we know what it's like, right? You bring down that risk profile a lot. It's really hard to land on surfaces, and it's really hard to maintain a lander for very long because you're in this radiation environment all the time. And so to spend billions of pounds, billions of dollars on a lander that might only last 2 days, that can be a bit of a hard sell, especially in a time where, like I said, it was an American lander concept, and yeah, there's not a lot of, seems like the administration is not really enjoying space science there very much right now. So yeah, we'll see. Yeah.
You briefly mentioned the ESA's JUICE mission.
Yeah.
It's also going to the Galilean moons.
Yeah.
Could you explain the differences between JUICE and the Europa Clipper?
Yeah. So JUICE is the European mission that's going to the Jupiter system. It launched just before Europa Clipper. It arrived just after it. It's got a slightly different orbital trajectory. But its main focus is Ganymede. So it's a different moon of Jupiter. Ganymede, it's really got an interesting history. We think it's got its own magnetic field, so it means it has probably a liquid, molten core. Probably, maybe is an ocean world. So a really interesting thing in its own right. It too, will be in the Jupiter system, and we'll be looking at other targets, I'm sure. And so it has 2 flybys of Europa. Europa Clipper has a couple of flybys, if not more, of Ganymede. So there's a lot of immediate science that can be done. But I was also on the steering committee that looked at how science could be improved for both missions by talking to each other. So an obvious example perhaps is the magnetospheric science. So if you have 2 data points in a magnetosphere, that's much better handle on what's going on than just one. And so we were trying to think of ways that both missions could be more than the sum of its parts by having 2 missions at the same time. Another one perhaps is the plumes. So we said that they might be sporadic. You can imagine a scenario whereby one spacecraft saw them go off, which would be a huge result. But the general consensus was, let's play nicely and talk to each other. Don't just hold off and make it a press release, so that the other spacecraft could look at it as quickly as possible. So, those sorts of things about improving communication and collaboration is really important. JUICE is going to be really fun, I think. And it also has a radar, so it's going to give us some really nice ice measurements of Ganymede, which I'm pretty excited about. And the more we understand about the whole system, the better. Sorry, you're lurking. Sorry. No, I'm done. Go on.
Okay. So I'll have to cut off the questions here because we are at 4 now. but feel free to come down and ask.
Sure.
If that's all right. And I'd like to thank Professor for the wonderful lecture, and thank all of you for coming on this busy Thursday afternoon. And as a gift, we have some donuts outside, which you guys can help yourselves to. So, yeah.